This unit is a relatively short unit. I'm not sure where the exam is going to land. If the exam happens to land after a weekend, that's fine, because the upcoming weekends are only 2-day weekends. And I think sometimes that's the way the cookie crumbles, and that's what we have to deal with. So this is dealing with Chapter 3. Unit 2 is Chapter 3. We're going to start off, this is about polynomial functions, learning today in a very general way about the characteristics of the graphs of polynomial functions. The graphs of the functions that we look at are not going to be things that you have to know exactly how to find the features of, but there are certain features of them that you need to be aware of. We're going to start off by defining a polynomial function so you know how to recognize one. There are some terms that we need to be able to apply for a number of reasons. One is degree of a polynomial function, one is leading coefficient of a polynomial function, and one is the constant term of the polynomial function. Because those three things are going to tell us something about what the graph looks like. Not a detailed picture of the graph, but it gives us a starting point. The details will be revealed in further units. And we're also going to be looking at what these graphs look like in terms of the number of zeros, or x-intercepts. So polynomial functions cross the x-axis sometimes. And knowing how many places they cross the x-axis in is knowing how many zeros there are for the function, which is important. I want you to notice, though, this word possible. So by looking at certain information with the equation of a polynomial function, you cannot necessarily tell me exactly how many x-intercepts are going to be, but you can tell me something like, well, there will be at least one, but there could be 2 or 3 or 4. And I know that seems very non-specific, right? Or you could say, you know what? It's possible for the not to have any x-intercepts, or there could be 1 or 2 or 3 or 4 or 5 or 6. There are different rules that we have to follow to answer those questions. We're also going to be talking about general shape and something which is called end behavior. I can tell you right now what end behavior is. When you look on the left-hand side of a graph and on the right-hand side of the graph, and you look at where the ends, the left and the right ends, point, that's end behavior. End behavior will either look like this. Both arms, left and right, will go up, or both arms will go down, or the left will go up and the right will go down, or the left will go down and the right will go up from your perspective. That's what end behavior is. So this is a pretty intimidating definition. A polynomial function is any function that can be written in this form. A sub n multiplied by x to the n. So this is called a polynomial term. And I'll get into more details about the notation, but this is just, for example, this could be 12x to the 4. So these a's are coefficients. Okay. One of the things that's important about all of these terms, and I'll explain the rest of this in a bit, is that all of these a's are coefficients. A sub 0, this number over here, is a coefficient. It's a number. It's a number. A1 is a number, it's a coefficient. And all of those coefficients are real numbers. And I hate that we have to say that all the time because you don't study non-real numbers. Non-real numbers are things like the square roots of negative numbers, which you might learn about in post-secondary. The leading coefficient cannot be 0. So all of these, let me show you this here first of all. These are all exponents. These are all just labels, okay? So when we say a sub n, we're just saying it's the a value for the first term. N is just a label. A sub 2 is the a value for this term that has x squared. And we're probably not even going to use those a's and those labels later on, as you will see. But the reason why I'm telling you that, that this coefficient here cannot be 0, well, that coefficient is what's called the leading coefficient. It's the coefficient that leads the pack. It's the coefficient of the term with the highest exponent on x. Okay? If that coefficient is 0, then guess what? This term doesn't even exist. So it's not the leading coefficient. The leading coefficient would be this, and we would call it a sub n. So don't get bogged down into too many details about some of the things that we're talking about here. The leading coefficient can't be 0 because if it is, then it's not the leading coefficient because there's no term there. Okay? It's like me telling you that I have a quadratic function of ax squared plus bx plus c, and a is equal to 0 and b is equal to 11, and c is equal to -3. Is that a quadratic function? Well, no, because if I put 0 in for a, I get f of x equals 0x squared plus 11x plus 3. Well, that means the function is this. It's not a quadratic function, it's a linear function. By the way, a quadratic function is a polynomial function. A linear function is a polynomial function. And the final note to be made here is that the exponents are whole numbers. In a polynomial function, you cannot have decimals for exponents, and you cannot have fractions, and you cannot have square roots. So in the end, and the example that we're going to look at should gel this in your head, you need to understand that these things are exponents and they are whole numbers. Maybe the first exponent is 12, and then the next one is 11, on and on down the line. These things are simply labels on the coefficients. The exponents must be whole numbers. The coefficients themselves have to be real numbers, which means they can be decimals or fractions or square roots, but just not square roots of negatives. So to begin with, which of the following are not polynomial functions? Well, I would like you to go through all of them and maybe just put an X through the ones that are not. Or write the word not, and then write the word polynomial if they are polynomial. And while you're doing that, just a quick note here. This is not an exam question. I don't think I would ever give you on an exam which of the following are polynomial. The point is you want to be able to recognize which ones are polynomial functions, because by the end of the course we've got a whole bag full of different functions. You need to know if it's polynomial so you can apply the math we learn in this unit. And the hint I will give you is there's only one here that's polynomial. And I would suspect that many of you would think none of them are polynomial. But the first one is definitely not polynomial. Who can give me a reason why the first one is not a polynomial function? Seamus. Say it a little louder. Right, there's an exponent that's not a whole number. You have an exponent of 1 over 3, no go. That's not polynomial. I'll tell you right now, I'm going to jump ahead here to this one, that C is not polynomial either, for the same reason that we have an exponent that's not a whole number. Whole numbers are 0, 1, 2, 3, etc. By the way, the exponent on x here in B is 0, which is a whole number. And I always remember whole numbers include 0 because 0, if you look at me, 0 has a hole in it. Okay? And until somebody told me that, it was a junior high math teacher, I think, I always mixed up which ones were natural and which ones were whole. Whole is 0, 1, 2, 3. Natural is just 1, 2, 3, etc. E is not a polynomial function, and this is a little bit more difficult to explain why that's the case. Does anybody want to take a stab at it? I mean, it just doesn't look right, does it? It doesn't fit the same pattern. I don't have a number times x raised to an exponent plus a number times x raised to an exponent. In fact, anytime you have the x in a denominator, it's not polynomial. It turns out it's called a rational function. We'll learn about that in a few months, couple of months. This is not a polynomial function because the coefficient of the first term is the square root of -3, which is not a real number. Now, and you have to be careful with b and d, these square root signs in b and d extend over the coefficient and the variables. Which means I could write this as f of x or y equals the square root of 3 times the square root of x cubed, and then minus 5x plus 2. Here, I can write f of x equals the square root of 3 times the square root of x to the 4 minus 5x squared plus 2. There's only one difference here, and that's that exponent on x under the square root. This one is not a polynomial function, but d is. And the reason has to do with your understanding of what a square root means. When you have a radicand that's under a square root, that's the same as raising it to an exponent of a half. This is what root r means. They mean the same thing. So in b, we have the square root of x cubed, which is x to the half, which is x cubed to the half. That's what we have in b, in part. There's other stuff in b. When you look at d, we have x to the 4 to the half. Well, you've learned in various courses, grade 9 and 10, that when you have a base raised to an exponent and then the entire thing is raised to an exponent, that you multiply the exponents. And when I take 3 times a half, I get 3 halves, or 1.5. When I take 4 times a half, I get 2. And 2 is a whole number, but 3 over 2 is not a whole number. Which means that this is a polynomial function, because it can be written as a number times x squared. It's fitting the pattern. All right. Let's take a look now at the next part of this lesson. The degree of a yes?
Does it not matter if the exponents don't go down like n minus 1 and minus 2?
Thank you. I was going to point that out earlier when I talked about this. If I understand what you're saying, it doesn't matter that the exponent goes down by 1 or 2 or anything. For example, as long as they're whole numbers. For example, when I go back to this, if I have that is a polynomial function. Were you asking, doesn't it matter that I don't have x to the 11 and x to the 10? And no, it doesn't. As long as I have some polynomial terms, and they're all polynomial terms, then the function itself is polynomial. So this is a polynomial function. Let's go through the criteria. Are all of the coefficients real numbers? Yes. Are all of the variables raised to whole numbers? Yes. That's it. Those are the conditions. You have to have numbers times variables raised to whole numbers. And the fact that we have n, n minus 1, n minus 2, n minus 3 means we could have every single exponent from the highest degree to 0. Or maybe we only have the highest degree and that's it. Or maybe we have the highest degree and a couple others. Have I answered your question? Okay. All right. So the degree of a polynomial function is the highest degree of any term in the polynomial function. This goes back to grade 10, actually. I think you're taught this in grade 10 and then you forget about it. The degree of a polynomial term is the exponent on the variable. In the example that I just gave you, the degree of this first term is 12, the degree of the next term is 2, the degree of the third term is 1, and the degree of the last term is 0. Those are degrees. And what I'm telling you is the degree of a polynomial function is the highest degree, which means this is a degree 12 polynomial function. Okay? It doesn't matter what else is there. The highest degree rules the roost. The leading coefficient is the coefficient on the term with the highest degree. So we would say in this example that I've written that this is a degree 12 polynomial function and the leading coefficient is 4. The constant term is the term that is not dependent on x. It's the constant term. No matter what x is, there's a term that's always the same. The constant term here is negative 3. I mean, I put that x to the 0 just to make a point about exponents, but that constant term is negative 3. All right, so let's take a look at an example now. Identify the degree, leading coefficient, and constant term. So take a second and write out the degree, leading coefficient, and constant term for example 2a. There's a little bit of a twist to it. And that little twist is that there's no rule that says you have to write the terms in a particular order. And when we take a look at this polynomial function, there's a term with a degree 3. So it's wedged in the middle even though it's the highest degree. So if we wrote this kind of in a standard practice way of writing things, we would probably write negative 25x cubed plus 34x squared plus 2. But we want to focus on the term with the highest degree, which is negative 25x cubed. That means the degree is 3, the leading coefficient is negative 25, and the constant term, of course, is 2. And I was going to mention this earlier just a few minutes ago, but I said the constant term is the term that's always the same. If there is no constant term, then the constant term is 0. You could always write plus 0 at the end. If we wanted to figure out the degree, leading coefficient, and constant term here, what we would do is we would, well, multiply out these two binomials using FOIL, I guess. 15x squared is my first. Outer is the 3x times the 2. Inner would give me negative 2 times 5x. And last is negative 4. So what is the degree? Well, 2. The leading coefficient is 15, and the constant term is negative 4. I just want to point out to you that you could have answered that without doing the outer and inner product. And I want to make this as general as I can by telling you that the highest degree term, and I have a more complete example of this that I will show you in a few minutes, but if you want to know the highest degree term, and I want to make a point here that this is in factored form, and this is in expanded form. And the highest degree term is the highest degree term in the expanded form. That's what we're after. Factored form means you have things multiplied together, factors multiplied together. I want to point out to you that the highest degree term in the expansion is the product of the highest degree terms of each of the factors. So what is the highest degree term in 3x minus 2? 3x. What is the highest degree term in 5x plus 2? 5x. Which means the highest possible product you could get is the product of those two highest degree terms. On the other hand, the constant term in the expanded form has to be the product of the constant terms in the factored form. And it doesn't matter how many factors there are, that's going to be true. For example, with this one, what does this mean? This means f of x is 3, and I want you to rewrite this and put the 3 in brackets. Remember, if you can put something in brackets and multiply it, that thing is a factor. And then 4x minus 1, and 4x minus 1, and 5x squared minus 2x plus 3. I don't think we want to multiply that all out. If you did, think about what this would involve. You would multiply maybe this out, and I'm not going to do all of this, but I'll do the first step, to get 3 times 16x squared minus 8x plus 1. And then what you would have to do is multiply every term in this by every term in this, performing 9 products. And some of them will be similar terms that you can add together. And you would simplify all that. Then you would multiply everything by 3. We wouldn't want to do that. The bottom line here is the highest degree term of this is going to be, and this is a little tricky, the highest degree term of each factor multiplied together. So when I look at factor 1, what is the highest degree term of that factor? 3. When I look at factor 2, the highest degree term in factor 2 is 4x. The highest degree term in factor 3 is 4x. The highest degree term in factor 4 is 5x squared. When you expand this out, you're going to get f of x equals, let's do this. Go ahead and multiply that out. I want to say 240 x to the 4. Okay? When you now look at, so this is the leading term. When you look at the constant term, well, you're going to multiply out the constant term in each factor. And the reason why this is tricky is in the first factor of 3, 3 is both the highest degree term and the constant term. Times -1 times -1 times 3, which I believe gives me 9. I don't think that's difficult. Yes? Okay. So what that means is we're going to have a plus 9 here. And the fact of the matter is, those two layers of bread are what tell us about the graph of the polynomial function. All the filling between them, all the stuff that's in between them, doesn't tell us anything directly about the shape of the graph or what the graph looks like. The degree is 4. The leading coefficient is 240. And the constant term is 9. So if I ask what the constant term of this polynomial function is, If I asked you what the constant term of this polynomial function was, you'd take 3 times -1 times -6 times -5. If you expand this out, it turns out that the first term and the last term, the leading term and the constant term, are what are important. The middle stuff is not really valuable. You would get, can you double check to see if my mental math is correct? For the product of 3, -1, -6, and -5. No, -90. My mistake. I had an extra factor of 2 in there for some reason. -90. And then you would get 12x to the 4. Because 2x times 3x times x times 2x gives you 12x to the 4, if I'm not mistaken. And there's stuff in the middle. Okay, so number 3. Here's a polynomial function. The fact that I wrote q of x doesn't matter. Could have written f of x or p of x or r of x. This is y equals 4. The question is, why is this a constant polynomial function? Why do you think we call it a constant polynomial function?
There's only a constant.
Yeah, there's only a constant term. That's one way to explain it. Y is equal to a constant. It doesn't depend on x. We can drive this home by saying, if I said to you, make a table of values, if you've ever had me as a teacher where we make a table of values, I always suggest these kind of boilerplate, standard issue numbers for x, and then you throw them all into the function and you find y. But there is no x. So when there is no x in the equation. So when x is -3, y is 4. When it's -2, y is 4. It's always y equals 4, which means the function has a constant value. Okay. What is the degree? Well, the degree of a constant polynomial function is 0. And this is an interesting point that you're not asked about, but I'll make it anyway. The leading coefficient of this function is also the constant term of this function. All right, now we're going to explore. First of all, when you have y equals some constant number, that is degree 0, and it's called a constant. Now, you remember a page back where we had a sub n minus 1, all that garbage? And I said we're not going to use it? Well, here's why. If I want a linear function, rather than me writing a sub n times x to the n plus a sub n minus 1 times x to the n minus 1, I just write ax plus b. And this, you should recognize y equals ax plus b as a linear function from grade 10. Except what did you use for a in grade 10 instead of a? You used a different letter. M, that's right. What did you use for b? Well, you did use b. Okay. For a quadratic function, linear is degree 1. For a quadratic function, that should be obviously recognizable to you. Y equals ax squared plus bx plus c. It's a degree 2 and it's called quadratic. Well, if we have a degree 3 polynomial function, we can write it as y equals ax cubed plus bx squared plus cx plus d. We've got another letter going on here. And the name for a cubic, or the name for a degree 3 polynomial function is cubic. We can go degree 4, that's called quartic. We can go degree 5, that's called quintic. Do you need to know these names? I would say for sure up to cubic. For sure. If you are asked to, on a written response, create a cubic polynomial function, you need to know what that means. I would say it's probably a good idea to know that quartic is 4 and quintic is 5, only because you might see those words on an exam, and I don't want you to be confused by them. This goes on and on and on. I don't know what the name is for degree 6. I've never bothered to look. That's how unimportant it is. I want to say hexic, but that doesn't sound right. All right, so now your teacher, that's me, I'm going to show you a bunch of graphs with different equations, and we're going to learn something about the leading coefficient, the degree, and the constant term. And you have a table where you're going to write your observations. And I'm not going to write them down. I'm going to explain things to you verbally. Okay, so here is a constant polynomial function. You can take a look in the top right-hand corner. You can see that its y is equal to 10. And I want to point out the most important feature, other than the fact that it's a horizontal line, is that it has no x-intercepts. Now, of all the rules we're going to learn, there is an exception to one of the rules. This is the rule. The x-intercepts is related to the degree. What's the degree of a constant polynomial function? 0. How many x-intercepts are there? 0. Okay? There's an exception to this rule for a constant function. Could a constant function have an x-intercept? Yeah. If its y equals 0, then not only does it have an x-intercept, it has an infinite number. Just shelve that exception away for now. Okay? Y equals a constant other than 0 will have 0 intercepts. What about something like y equals 4x minus 9? Well, that's a linear function. You learn about slope and y-intercepts of linear functions in grade 10 and even in grade 9. I think you study them a little bit. The point I want to draw your attention to is a linear function is a degree 1 polynomial function, and there's one x-intercept. Well, it's following a nice pattern so far that the degree of the polynomial function is the number of x-intercepts, but this is going to fall to pieces right away. There's more involved than the rule. Because if I take a look at this quadratic function, this is quadratic, which is degree 2. And, you know, in that box where it says quadratic, I hope you just know it's degree 2, but if you want to write degree equals 2, that's fine as well. And there are 2 x-intercepts. But does the graph of a quadratic function, and you talk a lot about this in Math 20, does the graph of a quadratic function have to have 2 x-intercepts? No. And we can explain this not from a Math 20 standpoint, but a translations standpoint in this course. If I take this function and I shift it up just the right amount, then I get the same graph, but it only has 1 x-intercept. And if I take that function and I shift it up even further, even just nudge it a little bit, it has no x-intercepts. So let's go back to the beginning. A degree 0, with the exception of y equals 0, a degree 0 has no x-intercepts. A degree 1 has 1 x-intercept. Let's stop for a second. Does a degree 1, a linear function, does it have to cross the x-axis? Yes. There's no other way you could draw a graph that's linear if it doesn't cross the x-axis. Somebody said one semester, well, what if it's a horizontal line? What if the slope is 0? Then it's not linear, it's constant. So degree 0, no x-intercepts, with that other exception, which messes everything up, but we ignore that. Degree 1 must have 1 x-intercept. Degree 2 can have 2 or 1 or 0. And I'm going to ask you a question right now. What is it about the graph of a degree 1 polynomial function that's different than the graph of a degree 2 that guarantees the degree 1 is going to cross the x-axis? Seamus?
The fact that it infinitely goes up and down.
Right. The fact that the arms are going in opposite directions vertically. One arm is going to go, in the example we have, is going down towards negative infinity. One arm is going up towards positive infinity. But a quadratic function is always going to have both arms that are either up or down. And that means you can move that graph someplace so that it lies entirely above the x-axis or perhaps below if it opens down. When we take a look, and this graph is going to be new, this is what a degree 3 polynomial function looks like. And if you're watching this on video, it's not going to play the same, but a degree 1 polynomial function always goes in one direction vertically from left to right. It goes up and up and up and up and up and up from left to right. A degree 2, and by the way, a degree 0, up and down doesn't have any direction. A degree 2, from left to right, goes down and then up. It has two directions. Degree 2, two directions. Or it goes up, quadratic, and then down. So degree 3 must go up, then down, then up. Three directions. And that's what this is doing. From left to right, it's rising, and then it falls, and then it changes direction again. Every time we add a degree, we add a direction to the graph. How many x-intercepts does this have? 3. Can it have none? No, because the arms are in opposing directions. If it goes from negative infinity on one side, say the left side, to positive infinity on the right, it's got to cross that x-axis. But could it have, it has 3, could it have 2? If I take this and I shift it up just the right amount, I can get 2. And if I shift it up even further, I can get 1. So this polynomial function can have one x-intercept. We're looking at where the graph crosses the x-axis. It can have 1. It can have 2. Or it can have 3. But it must have at least 1. Okay, let's go back to the beginning. A degree 0 does not travel in any direction up or down. A degree 1 will always travel in one direction, left to right, in terms of upness and downness. It always goes up, or it always goes down. A degree 2 will go down, then up, or up, then down. A degree 3 will go up, then down, then up, 3 directions, or down, then up, then down. Well, degree 4 must go down, up, down, up. And because it has 4 directions, those two arms are going to end in the same orientation. There's an example of a degree 4 polynomial function. The equation is at the top. Listen, you don't know how to come up with that exact shape. We're not talking about the exact shape. We're saying that because it's degree 4, both arms are in the same direction. And how many x-intercepts does this have? Well, if we count the places it crosses the x-axis, it does so in 4 places. Can it cross in no places? Yeah. If I shift that up enough, it doesn't cross. Can it cross? I'll work backwards now in 1. Well, if I take this current graph and shift it down just the right amount, the answer is yes. What about just 2? Yeah, and there's other ways I could have gotten 2. What about 3? Definitely. And it isn't a puzzle that you want to try to wrap your brain around. I'm just demonstrating to you that a degree 4 polynomial function can have as many as 4 x-intercepts, or 3, or 2, or 1, or none, because both arms are in the same direction. And I hope you're starting to see a pattern here, that the graphs whose arms are in the same directions vertically are the ones with even degrees. Degree 2, degree 4. We'll quickly run through degree 5. Here's a degree 5. If you take a second and count the x-intercepts, you should notice there are 5. If I nudge this up a little bit, I can get 4. If I move it up even a little bit more, I can get 3. Well, I moved it down in this case, a certain amount. I can get 2. or I can get 1. I cannot get 0, though. So what have we learned? If the degree is 0, that's the exception. It's a horizontal line with no x-intercepts. Okay? If the degree beyond that, higher degrees, is an odd number, then there must be an x-intercept, and the number of x-intercepts can be anything from 1 up to the degree. So how many possible scenarios can you have for a degree 7? There can be no x-intercepts, one x-intercept, not no. Odd means it has to cross. So a degree 7 can have 1 or 2 or 3 or 4 or 5 or 6 or 7 x-intercepts. Whereas an even degree can have any of those numbers up to the highest degree, or it can have none. That's the lesson to be learned here. There are a couple of other things, though, just to polish off this lesson. So, odd degree has to have this for the end behavior. I don't care what happens in between. You know, all that stuff when I write leading term plus stuff plus constant term. I don't care about that filler in the sandwich, in the polynomial sandwich. The arms in an odd degree polynomial must be in opposite orientations. So they could be like this, the way I'm holding my arms, or like this. If it's even, both arms must be up, or both arms must be down. This is what we talk about when we say end behavior. What about the leading coefficient? I'm going to show something to you now, and it's going to be a little bit of a visual assault on your senses. I'm going to put all of these graphs on here. And I'm going to hide the legend because it's just getting in the way. But I will tell you that every single polynomial function I've graphed here has a positive leading coefficient. And all of these graphs have something in common. And I don't know if you can see it or not. Well, all of them except for the constant. The constant really screws things up. And maybe what I will do is I will freeze this over here while you're looking at it. And I'm going to bring up a whole bunch of graphs that have negative leading coefficients. We're looking for, on the right-hand screen, which is not being recorded, we're looking for what all those graphs have in common. They all have a positive leading coefficient. These ones, and I don't have as many, all have a negative leading coefficient. And I think for most people, as soon as I show you that, you kind of figured it out. How many of you see what is going on here? What is it, Will?
The positive ones finish going upwards and the
Right.
negative coefficients finish going downwards.
So this is right now, I got to get this straight because I have two screens. Okay, so what we're looking at right now are all of the ones that have negative leading coefficients. And as Will said, the graphs finish pointing down. And I like that because we always think left to right. So when I scan these pictures left to right, all of these arms on the right-hand side are pointing down. A negative leading coefficient tells us the right arm is down, whereas a positive leading coefficient, I mean, this is really ugly, but all of those have right arms that are pointing up, so they finish pointing up. And that's another thing that you need to know, is that a positive leading coefficient will have a right arm that goes up, and a negative leading coefficient will have a right arm that goes down. What then determines the direction of the left arm, whether it's odd or even? Because if the leading coefficient is positive, and don't write this, But if the leading coefficient is positive and it's an even polynomial function, then both arms are in the same direction, which means the left arm would be this way. But if the leading coefficient were positive and the function is odd, it has a degree that's an odd number, then the arms are in opposite directions, so the left arm would be down. And there's one last thing that we want to talk about. What's the constant term? Well, a positive constant term means a positive y-intercept, and a negative constant term means a negative y-intercept. And I really ought to change this and just tell you that the positive term of a polynomial function is the y-intercept. Look, if I have this function, y equals 12x to the 127 plus 3x cubed minus x plus 10, and I say what is the y-intercept, you're going to put 0 in for x. The y-intercept is found by replacing x with 0. And if you replace x with 0 in that function, all you're left with is the constant term. It's a very important thing. That's it. This is all about, so this is why on the title page it says two things that are odd. Got the same shape. This was not a comedy, by the way. This was an actual movie. And I want to say 78 or 79. And that's, I mean, this was normal. People danced like this. And if you check out his shoes, I actually had a pair of those that I wore to my grade 9 grad. And if I can find a picture, I'd be happy to show it to you. If you're interested in watching the movie for kicks and giggles, that's what it's called. I think 1978 or 79.